Hello, welcome to Advanced Manufacturing, CAD Solid Modeling. This presentation may be a review for you. We come to these classes with different experiences, and if you are able to move forward with the projects, this should be just review. But we want to also focus on what the role of the CAD model is in the design space, especially from a quality standpoint. So there are a few nuggets in here that you may learn from. Okay, my name is Todd Frazee, and I'm with Sierra College's Advanced Manufacturing Department. Um, in this unit, it reviews the relationship between CAD and CAM, essential for modern CNC machining. You learn how models are drive the CAM process, and how engineering drawings define final tolerances and specifications for manufacturing. Through hands-on experience, you'll master both modeling and toolpath creation to translate design intent into practice in real world parts. By the objectives of this lesson is that by the end of this lesson, you'll be able to understand the relationship between CAD and CAM in the modern CNC machining process, apply CAD software to model parts and import designs into a CAM environment, and model in 5-axis CNC mill applications to industry standards, which is one of the student learning objectives of this course. Technical drawings. Technical drawings communicate the design intent of the designer for the design intent the designer had for the form, fit, and function of what they've designed. Technical drawings define the tolerance criteria for a design as well. And technical drawings are used for quality control to evaluate if a part conforms to the design requirements so that the part performs as expected. We have CAD and CAM, so computer-aided design, solid models. They facilitate the drafting of technical drawings. Now, when I first got into CAD, we were doing two-dimensional CAD, and the goal was to create a drawing. And then a little bit later, I worked for a company that was receiving a lot of those drawings, and we would do CAD modeling in order to do CAM programming. That is flipped on its head now with the advances in technology. You're starting with a solid model, using that to define the design intent, and then the model itself facilitates drafting the drawing. It also is used for definition of computer-aided manufacturing toolpath. Some of you have already taken courses on this programming, so that's a review for you. But CAM toolpath for computer-aided number control machines, it makes the process feasible today to operate very complex machines and systems. I operated a universal mill, Decal Maho, back in the early 90s, and our ability to program the machine was nowhere near what it is today. We're able to generate very quickly very complex toolpaths that would not be feasible to program manually. It's important to remember, though, the relationship between the CAD model and quality control. So unless otherwise specified, CAD models are reference and used only to facilitate manufacturing. Technical drawings define the acceptance criteria for QC. So if you make a part and you're arguing with quality control on whether it's right or wrong because the model was incorrect or not fully defined, you will lose. The drawing is the last word for the tolerances on whatever the part intent and definition was. The only exception, and there are a few companies adopting this, is that they've adopted a robust model-based definition program. When I say program, it's not software. It's a program for the company. When I was at Aero Metals, I wrote the model-based definition plan so that we could do work for Boeing Missiles in Space, which no longer creates drawings. But you have to have a huge apparatus to control revision, control quality, and it's not the easiest thing to implement. And everyone in your plant that's making the parts has to be able to access that three-dimensional information and know how to process it, all the way from shipping, receiving, to the welding department. So what I have seen is, even though this technology has existed for over 20 years, it's very slow to be adopted, and the majority of the companies are still operating off drawings. So the companies that are receiving information from these companies that are model-based definition approved, they typically have big drafting departments. So the first thing they do is take all the models, they redraft all of the definition, and have a quality check process so that the rest of their facility can function. So maybe we'll get there someday, but it's not here yet. So okay, so now we're going to go to Fusion to review some modeling concepts. So we're going to do some review of modeling. Our first part is going to be a revolve part, and it is called the rod. And the reason I'm going to revolve this is it's cylindrical. It could be developed in a different way, but if you suspect the part may be turned or goes on a lathe, or is going to be spinning around a rotary axis, it's likely that having that center axis could be setting up your model in a way that's conducive to that CAM process. So on lathes, it follows the profile, and typically on mill parts, I'll put features like this chamfer on as a separate feature at the very end so I can suppress them. On a lathe, it's helpful to have that profile in case you need to select on it to drive tool path on it. But you don't always know your approach depending on what you're making. So we're using Fusion 360. We're going to model this part, and let's get right to it. This should be review for most of you. To make it to this class, you typically have taken a Fusion class. But if you've been away from it for a while, this might be a good review for you. So the first thing we're going to do is open Fusion, and then we're going to save our file, and we're going to save it as the part number, which is 8DV 4700305. And then we're going to put either an underscore or a dash, follow the instructions on your tutorial for the actual modeling. And I'm going to put T phrase E, first initial, last name, and save this. Okay. Yeah, the advantage of saving this up front is it starts the auto recovery. If you do a bunch of modeling and then save the part, your auto recovery won't start at the beginning, and you'll lose work if you crash. Okay, so we're going to always start off in design space. We're making a solid model, and we are going to sketch. So we start with a sketch. The workflow is you create solids by using sketches. So we're going to select the sketch tool, and we're going to select the plane we want to draw that sketch upon. Now, if you're setting up a drawing, typically you select the front, and that becomes your primary view of what you will see on your drawing. If you are setting up for a lathe, typically you want the top, and that'll put the profile where it's conducive for turning. So we're going to go ahead and hit top, and we're going to use our line tool. And we always want to start on origin so that our model is anchored. And we're going to click on origin, which anchors the first line, and we're going to draw a horizontal line. And if the little blue icon shows up, it's an auto relationship. So we're getting, if I pop it there, you can see there's a couple parallel lines with some lines on it. That's going to force that line to be horizontal. Then we're going to go vertical from there, and then we're going to go to an angle. We're going to go horizontal and an angle, and if you hover over origin, you can get this hidden line looking tool, and it'll help you align things. Now, a lot of new people to parametric modeling, they spend a lot of time fussing with getting their sketch to look just right. You just need an approximation of the shape like I have here, and we're going to define the part's final size by using a combination of constraints and definition dimensions. Okay, so we don't need to be making sure the angles are absolutely correct when you're doing the sketch. Now I'm going to expand my sketch folder, and what you see here is sketch 1. It's the first sketch in this part, and it has a little pencil icon. That means it's not fully defined and you're working on it. Our goal is to have that pencil icon to go away, all the geometry to turn black in color, and a padlock symbol will show up there, a little red padlock, when we've met our goal. Okay, so what are we going to do first? We're going to put in, I typically put in constraints first, so I know this chamfer and this chamfer need to be equal in length. So I've made a relationship between those. This line is horizontal, this one's perpendicular to that, this one's perpendicular to this line, and we have these two equal in shape, in length, so that's all the constraints we're going to need for this. Next, we're going to go and we're going to put the dimensions in that'll define the chamfers. If we look at our drawing, we have a 2 times 30 thousandths 45 degrees chamfer, so we need to make sure that we're defining that. We go back to Fusion. We're going to make a dimension from the horizontal line to the endpoint of the chamfer. We're going to click, and it's 30 thousandths, so 0.03. Hit enter, and it's going to shrink down quite a bit. And then that did not set the angle, so we need to set the angle between the outside line and here, which is 45 degrees. And the relationship equal forces the other chamfer to be equal in length, but it does not set the angle. So we need to go back over there and set that one at 45 as well. All right. Now, the next definition we need to do is the diameter. Now, this is a revolved shape. So what's happening is we are going to spin this shape around the axis I have highlighted in blue to create the part. So the distance from this line and this line is a radius. If we look at our drawing, the diameter is a 1/2 inch. So what we need to define on our sketch is the distance between here and the center that we're spinning around is half the diameter, or a radius, so 0.25. Then our overall length of our part is 5 inches. So we're going to go back to our part, and we're going to select on the longest edge of the part, drag away from the part, select, and set it as 5 inches. We now have the perimeter defined, and a little padlock symbol shows up. That means we can make something out of this. Let's hit Finish Sketch, and we're going to use this command here. It's called Revolve. Okay, it spins around the center to make the shape. So we'll select the tool. It's going to ask for 2 bits of information. It looks like it auto-selected my profile, but let me just reselect it. So this is the profile we want to spin, and the axis of rotation is going to be the inner edge, which gives us a 360 degree spin. You have the option to change that angle, but we want a full 360 degree revolve so that we have a rod. We're done. And we're creating a new body. Let's hit OK. Alright, so there's our rod. Now let's go back to our drawing. There's one feature missing right now. Go back to the drawing, and we have a little flat that's made on this end of this. And that flat is 20 thousandths from tangency of the rod down, and it's 370 thousandths long. There's several ways you can approach this. I'm going to approach it by modeling on the end of the rod. So we're going to model on the end of this rod. We're going to put a sketch That sketch plane is going to be on the face of the rod. So we're going to draw like a half moon shape on here. And we're going to start with a circle. And that circle is going to be concentric to the rod. And then we're going to put in a relationship that circle is equal in diameter to the outside diameter of the rod. Okay, and it's there. There's a little, it's black now. Our sketch is currently constrained, but we don't want to cut away our entire piece. Now we need to draw a horizontal line. Okay. And the way I drew mine, it automatically has a relationship that it's horizontal. If yours doesn't, you'll need to select it and select this horizontal icon. Now we're going to use the trim command. We're going to trim the edges of our line to terminate where the diameter is. And remember, we have a full diameter circle here right now. Let's look at it from a 3D view so you can see it. We also need to trim off this part here. Okay. Okay, so that now gives us this half moon shape that we can use to cut across and make our flat. Now we have one entity that's still blue and our sketch is not fully constrained. Okay, so in order to dimension the difference between the tangency point and this line is we need to create a construction line. That construction line is going to go from the midpoint, make sure the triangle symbol is showing, and we're going to go up and we're going to go and click, and then we're going to select that line. We're going to right click on that line and we're going to make it vertical and make sure that that's vertical. Then we're going to right click on that line again and we're going to make it a construction line. We then drag the endpoint down and we use the coincident relationship and make it coincident to our arc. This allows us to dimension this construction line to give it height. So we're going to go from there to there, and we're going to go back to our drawing, and it is a difference of 20 thousandths. So we're going to put 0.02. Okay, so we now have a profile we can extrude away from the plane we're on to create a cut in the top of this part to make the flat we need. So we're going to use the extrude command. We're going to select the inside of the shape we're cutting with. It's going to default to creating a new feature. And what we're going to do is we're going to create a cut. And the distance we're going to go is negative 0.375. Okay, so that's the opposite direction. That is matching the it's 370. So 370, delete the 5 thousandths off the end there. 370 from that edge gives us the flat where it's supposed to be. You can see it modeled or rendered in red, and that's what's going to go away. And then we're going to hit OK. Okay, there we go. We have our first model. All right, let's go on and let's do a part that's created in a different method. It's a flat prismatic part. When you say prismatic, we mean rectangular. Typically made on a mill. Okay, so we're going to open a new design file and we're going to model this spring. Okay, so we're going to save it off just like the other one under the proper part number. Go back to Fusion. First thing we're going to do is save. Put in the part number. _T for AZ. Again, follow the instructions on your assignment. If you're modeling this part, don't follow this tutorial. Okay, so if we look at our drawing, we've got a rectangular part. It's 1.5 inches by 1 inch. It has a set of holes in it. And it's 25 thousandths thick spring steel. Okay, so let's start off with the rectangle. We're going to draw a sketch. We're going to do it on the front plane. We're going to start at origin. And we're going to do it on the front plane. And we're going to start at origin and we're going to just draw. We're actually going to start with a rectangle. So we start at origin, draw a rectangle. Now if you're machining purist, you could move it over here and then back left corner be your vise stop. But that doesn't matter because you can change that when it gets to the CAM side of things. Alright, so we have 2 lines that are black. That means they're fully defined because they're anchored on origin. And we need to make dimensions. We have 4 constraints. That means these 2 lines are horizontal. These 2 lines are vertical. And we're going to select one of our edges and put a dimension on there. And our dimension, according to our drawing, is 1 inch in that axis. And then we're going to put a dimension in the opposite axis, and according to our drawing, it's 1.5 inches. Alright, so we should have a fully constrained sketch. You could choose to put the holes in now, or you can put them as separate features. I'm going to elect to put them in as separate features. We're going to finish sketch, we're going to extrude, and we're going to go down and we're going to go the thickness of our material, which according to our drawing is 250 thousandths, as we see here. I'm sorry, which is 25 thousandths as we see here. And we'll go 0.025. And that gives our piece thickness. Okay, and we have our first shape. Now we need to put our holes in, so we're going to sketch on the top of the part. And if we go back to our drawing, we have six holes. It's implied they're on center of the piece by the center lines and the dimensions. We don't have a dimension from edge, and we have a spacing of 1 inch between the furthest holes and 480 thousandths along center line in the other direction. So because of the design intent of this is to have the whole pattern centered, we're going to go back to our model and we're going to model that. We're going to go from center point, which the triangle symbol means midpoint. The X means you're touching the edge. We're going to go from midpoint of one side to midpoint of the other, and we're going to do the same thing in the other axis. Okay, and those lines are not features, they're theoretical center lines, so we're going to convert both of those lines to construction. Now let's draw our circles. So we have 6 circles. 1, 2, 3, 4, 5, 6. Looks like Swiss cheese. You notice I didn't spend a whole lot of time on that. Hold the shift key down so that we can select all of the circles. And we're going to put an equal relationship. So if I make a diameter change to 1, it's going to change all of them. Now let's define the diameter. According to our drawing, those are 200 thousandths in diameter. So we take our dimensions, and it doesn't matter which one because we've now put an equal constraint, and we're making them all 200 thousandths. What I just demonstrate there is parametrics. So you're able to put in a relationship between the different holes, and the parametric part is when I change the dimension, it changes them for all the instances. Alright, so 4 of our holes fall on center line apart. So our next relationship is going to be, we're going to make a coincident relationship between this circle and one of the vertical center lines. And you notice it snapped right to it. And then we're going to follow suit with its mirror on the bottom. So those have to fall on the center line of the part. Now, all three of these holes are in line with each other. So we're going to go to the horizontal vertical relationship, and we're going to make them all horizontal to each other. Okay, so these three, if I were to exit the command, I can drag them up and down. The center one stays on the center line, but the other two have to be in line horizontally with each other. Let's do the same thing with the one on the row on the bottom. Okay, so they now all have to be in line with each other horizontally. Now what we can do is we can do the same thing to make them these two holes are in line with each other vertically, and so is these two. Now we've got these set up so that no matter what the dimensions and the spacing are, this hole, the vertical holes have to be in line with each other, and horizontal they have to be in line with each other. Now let's throw in some dimensions. So if we look at the part, the horizontal spacing between the furthest two holes is 1 inch between these, centered about center line. So we're going to do a dimension between the center of the left hole and the right hole, and we're going to pick and we're going to do 1 inch. One inch, not 10 inches. Okay, so they're 1 inch apart, but what's not constrained here is they're supposed to be centered on the center line. Now there's debates on whether the drawing that we're working from is fully constrained. To do it the way the drawing is shown, we would need to draw a center line between the two holes and center it on this. Or what we can do is do a dimension from center line to one of the holes and make it half of the spacing between them, which is ½ inch. The net result's the same. Now we need to do the same thing for the vertical. Our drawing shows that the circle here and this circle here, row of circles, is 480 thousandths apart. So we're going to go back to Fusion and we're going to put a dimension that places them 480 thousandths apart. You notice though it's not centered. So we're going to do another dimension from center line to the center of the hole, and that needs to be half of 480 thousandths, which is 240 thousandths. We now have our pattern defined how the drawing shows it. The drawing doesn't have these two dimensions on it because it's implying that you know that these are centered on the space. We have our constraint paddle lock that shows up here. We can now hit finish sketch and we're going to punch these through as holes. So we're going to use the extrude command. We're going to select the volumes of what we want removed, which is the inside of each circle. And then we're going to do a cut, and we got to go in the negative direction. Okay, so we're going to type in, we're actually, instead of typing a number in, we're going to go through all. We're going to go through all of the material, and we're going to flip the direction of the arrow. So when we have this set up correctly, you should see that it's punching through, and you see the red line and the blue volume is what's removing. This is another power of parametrics. We are telling it no matter how thick this material is, these holes go all the way through it. Later, if I go change the thickness of this material, it'll automatically adjust the holes to the correct size. Let's hit OK, and there's our part. Alright, that concludes the modeling part of this demonstration. Okay, let's return to Fusion and we're going to review some quick milling CAM concepts. Okay, let's bring this together, and we are now going to do a little bit of CAM programming on this. The example is not going to be 5-axis, it's only going to be 3-axis, but just to make sure we're cementing in that how we approach this. I would typically water jet or laser cut a part of this type, perhaps on a plasma cutter with a fine tip. But these holes are fairly small, and depending on how you hold it, you could drill it. For this, I'm just going to do a quick example of how we go from CAD to CAM. So we're going to switch from the design package to the manufacture package. And we have different types of processes across the top here. So we have milling, turning, additive, inspection, fabrication, and utilities. Okay, so if we were to cut this part, say on a water jet, one method to programming is we would go to fabrication. And you would use the cutting tab, which only has a 2D profile command. This is a milling class, so even though it would be a little difficult to mill something this thin in spring steel, we're going to go ahead and just do one operation that mills all this. Two operations that mills and drills this. So just for the concept. So we start off with a setup. We first need to create a setup. So we're going to create a new setup, and this setup should be named something that is recognizable as the part, and it creates a stock volume of what we're removing to make this part. It defaults a tab where you're going to set the origin for your part. Typically, I like to define the stock before I define where my origin is. So I'm going to pick on the second tab, which is stock. And right now, it's just adding relative stock around it based off the parameters you see here. So it's using a relative size box, and it's adding 40 thousandths to the top and bottom and the sides of the part. I don't know, that might be how you want to approach it. In this case, let's assume that we're going to have our material start out the same thickness as what we're going to make, and so that all we're doing is profiling. So to do that, I would switch to stock on all sides, which allows us to adjust each direction. So let's add, we need to hold it down with something. Let's add 1/4 of an inch to X and Y. Yep. And nothing to Z. Now you notice it made it really thick. That's because we need to set our orientation. So right now, what is currently the y-axis is going to be our z-axis. There you go. I should have approached that different. All right, so we're going to use z-axis and axis plane. We're going to pick the top plane, and this pops our x-axis. It should be our horizontal axis on the table. Y in a relationship to the primary spindle. The z is up and down. And you notice now our stock is 1/4 inch wider, but the same thickness as our part. Okay, so that's what I punched in here. This is thin sheet metal. I'm assuming we have to clamp it on the edges, yeah, or tape it down, or some other method here. So we've got a stock width, if we were to go cut it, and this is the size we want, would be 2 inches by 1.5 inches and 250 thousandths, or sorry, 25 thousandths thick. We go back to our setup. We're doing milling. We have our orientation set. For the purposes of what we're doing, the model is body of the model is our model. What's rendered in yellow is stock. We don't have a fixture, so we'll minimize that. We're going to go over to post-process, and this is where we would put our program number. So we're going to just leave it at default, but You need a unique number to separate from other programs on the controller. In our comment, it's going to be operation 1 clamp on margin. What this is going to do is it's going to put that program comment in the program in the controller, and we're going to use our work coordinate system default, which is 0. We hit OK. So now we have this set up for stock. This defaults at setup 1. I'm going to call it op1. So when we do our setup sheets, it's abbreviated. And now we're going to select a milling cutter to cut the holes in the center. So we're going to go to 2D. We're going to do a 2D contour. We're going to select a tool from our VF1 library, 16th flat end mill. And we'll go ahead and take the default feeds and speeds for this example. We're going to go to the multi-axis tab. We're not going to do anything because we're not doing multi-axis. We're going to go to the geometry tab, and we're going to select what are we machining. So order of operations, we want to machine the inside of these before we separate it from the clamping material on the outside. Select each of those holes. We've got an arrow on each side on the interior of the circle for each feature. Now we go to the heights tab, and this is going to generate the different planes for the different safety zones for the cutter, and areas we're machining based off the stock we have. So we have our tabs. So we have our retract height and our feed height. So when the tool is in those zones, it's going to be moving as fast as a machine can go, what's called rapid. Then we have our top height, which right now is set as the stock top. So it's the top of the stock parameters. In this case, it's the same as the model top because we made our stock the same thickness as the material. And that's the point at which it's going to slow down and go to our feed rate, and whatever the feed height setting here is where that's going to start. So it's at 200 thousandths above the part. It's going to go from rapid to slowing down to feed rate. Then where am I cutting to? I'm cutting from the stock top, and it defaults to selected contours. You notice I selected the contours on the bottom of the part. Because I did that, it's going to cut all the way through. Okay, we're going to go to our next tab. We always want to select where. That allows for cutter compensation. For the rest of these, for this part, it's semantics, it's so thin. We're just going to leave all these at default for this example. Then we'll go to the next tab, which is linking. This gives you different parameters for lead in, lead out. Again, you're going to want to set these depending on the geometry you have. And we're going to hit OK. So now you can see the relationship between the model and our toolpath. It followed the model. What you see is these little nuggets in the center or pieces of material that will drop out. Now I want to do another operation to cut the outside of the material. So I keep op1 highlighted. I'm going to do another 2D contour. And this time we're going to use the same parameters we used before. They should be retained from the last operation we did. So we're going to select the geometry of the bottom perimeter. Make sure the arrow's on the outside and select OK. And this previews what our finished part should look like. Alright, so that's a quick demo of the relationship between CAD and CAM. Just because I programmed this off a model, the methods may not be sound. You might have cutter flex. You still need to measure it to the drawing and make your program make good parts. Okay, in this unit we reviewed the relationship between CAD and CAM, and it's essential for modern CNC machining. And you learned how CAD models drive CAM processes and how engineering drawings define the final tolerances and specifications for manufacturing. By the end of this lesson, you were able to understand the relationship between CAD and CAM in a modern CNC process, and apply CAD software to model parts and import designs into CAM environments. And model CAM in 5-axis CNC mill applications to industry standards. All right, we have several projects for you to practice on this lesson, and they do have several drawings, so reference Canvas for your assignments to model several parts that we'll be programming later in the semester. Thanks a lot.